Okay, what I'd like to do right now is take a look at some of the geometrical properties of the parabolic trajectory in terms of things that are known from classical geometry. So this comes from a problem book by Gnaddig. It's actually the second problem book of 200 physics puzzle problems for people to work on. This is problem 9, or it's adapted from that. The question is, given our usual setup, so we have a projectile that's launched on level ground, speed v naught. The launch angle, we'll say, is theta. I want to know what is the focus of the parabolic trajectory that is traced out in space. I also want to know what is the focal length of that, where is the directrix of this parabola, what is its latus rectum or semi-latus rectum. I also might want to know how far is it from the launch point to the focus. That might be of interest. Maybe we can even connect this to some other physics, for example, looking at conservation of energy. Our second problem that we'll work out is what is the centroid of the area that is spanned by this parabola or parabolic arc. That is effectively the center of mass, if you will, or at least the geometric average location for the area as such. Because this object is not rectangular, there's less area up top than there is below, we know that this centroid is going to be somewhere lower than the halfway mark, and we might want to know where that is. So let's start with this first question. To analyze this problem, let's draw a few additional lines or segments onto our diagram using some of the geometrical facts that are known about parabolas. And one of the most important things that's known about parabolas is that if you have incoming, say, rays of light coming in from the bottom, parallel to the symmetry axis of the parabola, they will reflect off of the parabola directly into the focus. So in particular, let's imagine some vertical beam of light coming along the negative y-axis. We know it will reflect off of the parabola at this location and then go directly into the focus, as direct as I can make it. Because this is a reflection, this red line that is spanned by my initial velocity vector actually is tangent to the parabola at the origin. And so we can note that this angle, which I'll call phi, and this angle are congruent. That's what makes them reflection angles. Both of these make these blue lines make the same angle with this red line, which is tangent to the parabola. Of course, we can also see by this that this vertical angle to the lower phi is also phi. So this angle above this blue line from, we'll call this point P, to the focus is 2 phi. Let's draw another segment in here, which cuts the parabola in half. And notice that if this is 2 phi, then this angle, say PFC, is also 2 phi. If you're one of those people that pronounces it phi, that's okay too. They're the same. Now we get a nice little triangle in here. This is a right triangle. We know that the base of this right triangle is half the range, again by symmetry. Let's call this distance between point P and point F, say, D. We might want to know what that angle or what that distance is. Well, using this triangle right here, and in particular looking at the sine of this angle 2 phi, we can see that it is the opposite side, r over 2, divided by the hypotenuse, which is d. But we have a formula for this r. Remember, that's the maximum range of this projectile. I should say maximum range. It is the range of this projectile. Notice that that's given in terms of theta, not phi. So we could rearrange this to find what this d is. It would be nice if we could simplify this more by interjecting a little bit of information about these angles. Notice from our diagram that the green angle theta, the launch angle, and the blue angle phi are complementary to each other. They do add up to 90. I'll write things in degrees for now. Okay, well, let's try replacing this phi with 90 and see what happens in that sign. Well, this is just the same thing as sine of 180 minus 2 theta. And you might recall a cofunction identity or a shift identity for sine, that sine of pi or 180 minus some angle is the same as sine of that angle. In other words, sine is symmetric around pi over 2. It's symmetric around 90. If you want to prove this more directly, you could, of course, apply the difference formula for sine, and you'll see that you do indeed get sine of 2 theta. So if sine of 2 phi equals sine of 2 theta, we can replace this with sine 2 theta. That cancels with the part that came from our range formula, and we end up with this remarkable result that this angle, or rather this distance, between my focal point and my launch point is independent of my launch angle. It's always the same distance, d. While we're at it, you might notice that this kind of looks suspiciously like some sort of kinematical quantity. For example, if I multiply top and bottom by m, say the mass of this projectile, I would have 1/2 mv squared, or v naught squared, divided by mg. So this really is energy over weight. In other words, you can kind of think of this distance as some kind of specific energy. Now notice that 1/2 mv naught squared is the initial energy, but if energy is meant to be conserved, this particular quantity should have some connection to other points on the graph, which we'll see shortly. The last thing we'd like to do is now find out, well, maybe where is the height of this focus? I know by symmetry that it has an x-coordinate of r over 2. How would I find that vertical component? Well, the vertical component is again going to come from trigonometry. Now that I know how I can relate this 2 phi to that distance d, maybe I'll call this distance, say, move that over, yf, something like that, the y coordinate of the focus. We can see from this diagram that the height of the focus is going to be d, which we've already determined, times the cosine of 2 phi. We would like to rewrite that in terms of the launch angle theta instead of this angle with the vertical phi. So we could follow a similar argument to what we did here. I'll just leave it for you to show that it's not quite the same. We do actually pick up a negative sign in this case. Again, you can apply the angle addition or angle subtraction formula for cosine to show that. So that means that my yf is negative d cosine 2 theta. You might be a little surprised that a negative shows up here. After all, that sure looks like a positive value. Well, it will depend on your launch angle. What this is really telling us is that for launch angles that are 45 degrees or greater, or let's just say launch angles that are greater than 45 degrees, I'll end up with a cosine of an angle that is bigger than 90, meaning a negative. Negative, negative will give me positive, and you will end up with a picture like this. It also tells us that if my launch angle equals 45 degrees, this focal point lies on the x-axis. It'll actually be at the same altitude as my launch point P. And if theta is less than 45 degrees, the focus will actually be below the horizontal axis. There's nothing really wrong with that. I'm not expecting my focus to always be in a positive direction, but I am expecting it to lie on this line at r over 2. Okay, so we found the focus. Now let's find the focal length. Okay, so here are the coordinates of our focus, our focal point. As a reminder, here are the coordinates of the vertex. This is the location where this parabola has its maximum height. We worked out the maximal height formula earlier. Again, this d is v naught squared over 2g, a fixed constant that's also the distance from the launch point to the focus. The next thing I want to calculate is the focal length. Now the focal length is actually this distance here. I'll call it little f. The distance from the vertex to the focus. I want to know what that distance is. That's really easy. It's a vertical line segment. I just have to subtract the two vertical components of those 2 points. Notice I am subtracting a negative there. Let's go ahead and use one of the double angle formulas for cosine, because we've got a nice sine squared here that we might be able to combine this with. Now there's a bunch of double angle formulas for cosine 2 theta, or double angle formulas for cosine theta. And so I want one that'll play nicely here. Let's go ahead and use the one that is cosine squared minus sine squared. Sure enough, the sine squareds cancel out, and I end up with d cosine squared theta. So that is my focal length here, and we can see that it does change a bit with angle. In fact, when theta is 90 and you fire this directly up, the focus and the vertex of that parabola are the same location. After all, you don't really have a parabola, or it's a degenerate parabola. It's a ray that has a maximum point at V and then has a single ray extending down along the y-axis. Okay, so that's our focal length. We can also answer some other questions about the geometry of this object. For example, there is a line, or segment rather, that passes through the focal point that is perpendicular to the axis of symmetry of all parabolas. And this particular line is called the latus rectum. I might want to know how long is that. It turns out that this distance p is the semi-latus rectum, it's half, and this happens to be exactly twice the focal length. I'll leave it in some high school geometry to prove why that is. So we can find that the latus rectum has a length of 4 times this value. Again, it will depend on theta. We also might want to know where is the directrix of this parabola. Now, the directrix is a line that's very important in the geometry of parabolas. In fact, the definition of a parabola geometrically is it's the locus of all points that are an equal distance from a given point, the focus, and a given line, the directrix. So in particular, there will be a line, it'll be up here. I'll call this line L, the directrix, such that any point on the parabola, let's just take point P for now, will have the same distance to point F as it does to this line. Since we've already worked out that that distance was d, that means that this distance from point P up to the line, of course distance to a line meaning the perpendicular distance, must also be d. Well, then the equation of the directrix is very easy to write down. It's the horizontal line y equals d, or y equals v naught squared over 2g. And using this geometrical property of parabolas, we can now really interpret this directrix as effectively a line of constant energy density. Because any other point that I take on this parabola, let's say I take a point, I don't know, maybe here. And I know that at this point, there will be a velocity vector. Maybe I'll call this v1 or something like that. There will also be some distance. Maybe I'll call it d1. And there will be some height. I'll call this y1. But notice, again, that this distance and this distance must be the same by this property of parabolas. Well, that means that we can calculate some of these distances in a couple different ways. On the one hand, we can easily see that this d1 plus this y1 is equal to the original d. And secondly, using the exact same setup that we did earlier, I can relate this d1 to v1. After all, d was related to v naught using a particular geometrical argument. There wasn't really anything special about that point. I could have taken any point here and looked at the tangent and looked at the angles and found the double angles and all of that. And so we could show that this d1 is also v1 squared over 2g. In other words, it will depend on the speed of this object at the point where it is. Well, if I just do a little bit of rearrangement here, we get this very interesting relationship. V1 squared over 2g is equal to V naught squared over 2g. Let's recall that was the original d, minus y. In other words, how high is the projectile at this particular point? Let's multiply everything by 2g and maybe move the y1 over. And lo and behold, aside from missing m, the mass of this object, I have the equation for conservation of energy. The initial total energy, with an m there, would be only kinetic energy. It starts at the ground. Any final total energy would be a sum of a kinetic energy term and a gravitational potential energy term. Notice that this v1 is the speed of this object at various points, and this was completely generically chosen. So the geometrical property that defines the locus of points spanned by a parabola is no more than the physical concept of conservation of mechanical energy. Okay, so we have a nice handling on the parabolic properties of this trajectory. Now let's turn to a different question and try to calculate that centroid. Okay, so now we want to calculate the centroid of this region under the parabola. Recall previously we've actually calculated the area under a parabola. We found this result, if you want to write it in terms of the launch angle. Might be a little cleaner this time though, just to write it in terms of the launch angle and the maximum range directly. So remember that, again, maximum range meaning the range. Remember that r does depend on theta directly, so you can go back and forth between these two. We also need to recall the trajectory equation for our parabola. I think the cleanest way to write it in this case is to factor out the tan theta, and then you have an x times a 1 minus x over r. You get the two intercepts very easily from that, and it recovers our inverted parabola. We now want to calculate the centroid. Now this is a location in space. By symmetry, we can instantly say that the x component of the centroids, which I'll write as x bar, is just half the range. So symmetry makes that easy. The y component is the one that's got a little bit more meat to it. So let's recall how to calculate the centroid of a geometric area. We'll be using some calculus here. Of course, there are a few geometric ways of doing this that don't involve calculus, but I think this is the most straightforward route and what you might have seen in a calculus class. So we have 1 over the total area. Remember, centroids are effectively weighted positions. Here we're weighting by area because we have an area of our object. And then I'll integrate the y-coordinate upwards along my whole integral, or along my whole trajectory, weighted by little strips of area. Now, since this is an area integral, it's probably going to be easiest to write this as a double integral. And we'll use Cartesian coordinates. I'll go ahead and write my double integral by doing y first, and then we'll do the x integral. Looking at the region that I'm integrating over, well, my bits of strips of area in the y direction will go from y equals 0, of course, which is along the base of this parabola, up to the parabola itself. It's this y of x function that we have right here. The x coordinates, to find the entire area though, or at least to weight against it, will go from the origin all the way out to r. Okay, well, this first integral is real easy to do because we already have it written in terms of y. The antiderivative of y will be 1/2 y squared. And of course, plugging in our y of x coordinate and 0 into the fundamental theorem of calculus, we'll just leave this as y of x squared. Now let's go ahead and start plugging in some of our values. So a, I'll write it again in terms of r. I think that'll be easiest. And y of x is this whole bit, which I'll also write in terms of r. Okay, a lot of this stuff is constants that can come out to the front. So for example, this 1/2 and this 1/6 can combine to give me a 3. This tan squared is constant with respect to x. It can cancel one of these tangents, so I'll be left with a tangent in the numerator. I can also pull out, or rather, I can also maintain that r squared in the denominator. And then it'll be pretty convenient to make a change of variables here to, let's call it u, which is x over r. That's pretty common whenever we see something like this, x over r. Also, because my bound starts at 0 and goes to r, it's a way of non-dimensionalizing this integral that'll be convenient anyway. So let's go ahead and make that explicit. So maybe over here, I'll write down the details of our substitution. When x is equal to 0, u will also be 0, and when x is equal to r, u will be 1. My x squared here will end up being r times u squared. This will become 1 minus u squared, and don't forget the dx will also pick up another r. Notice that I have an r squared here and another r here, which will partially cancel this r squared down to just an r. I should expand out this binomial just to make my life a little easier. I'll have a u squared times 1 minus 2u plus u squared du. Okay, we're pretty much done. Let's go ahead and just bring this to the top, and we will complete this calculation of the centroid. Okay, I think on the previous board I did not include my tan theta there. Of course, that was coming along for the ride. So this is the integral that we want to do. It's pretty straightforward, just power rules all the way down. Of course, plugging in u equals 0 gives me 0. Plugging in u equals 1 will just give me a 1/2. Sorry, 1/3. 1/3 minus 1/2 plus 1/5. That ends up being 1/30. That 1/30 will partially cancel with the 3 here. Now we could leave it in this form. That's totally fine. We could also rewrite it in a number of different ways involving only the function of the launch angle. That's okay. We could do that. Let's go ahead and actually rewrite r. I'll remind us what that was here. I'll also expand out the double angle just to make life a little easier. And we can see that when we multiply this by tangent, the cosine cancels out and I get a sine squared. This 2 also becomes a 1/5. One thing that might be kind of nice to note here is that this centroid can be written in terms of some fraction of my maximum height, which earlier we had calculated using a sine squared. It had this extra 2 here, though, which this does not have. So this is the same thing as 2/5 of the maximum height. 2/5 is indeed less than a half, so the centroid is below the halfway mark, which kind of makes sense in terms of where the area under this is distributed. Okay, so we have our centroid location. It's the ordered pair r over 2 for the x coordinate, and then maybe 2/5 of the max height in the h coordinate or in the y coordinate. Or you could rewrite it a number of different ways if you want to write it in terms of, say, launch angle, etc. This knowledge of the centroid might come in handy for maybe calculating some volume of revolution. Maybe we'll do that in the next video. So there's our centroid. We've completed our 2 problems. QED.
Now I know that this video is already a bit too long, but I couldn't resist making a little Desmos simulation and looking at the vertex, focus, and centroid of our projectile motion. And notice that because the focus is always a constant distance away from our launch point, regardless of angle, that's the same thing as saying that it must lie on a circle of radius d. We can also see this by the parameterization with this sine 2 theta and negative cosine 2 theta location. So as we change the launch angle, we see this focus kind of trace out a circle of that constant radius d. It's kind of nice. The centroid does not trace out a circle, it traces out an ellipse. But it's just kind of fun to see the geometric interpretation of that. And we might also notice that our launch angle does determine where our parabola lies, but it also tells us that there's some kind of envelope shaded in purple here that encompasses all of the points that our projectile could possibly reach, at least above the ground. And it might be interesting to figure out what that region of attack is. So maybe we'll do that in a future episode.